Valence shell electron pair repulsion theory, in short VSEPR theory. This topic comes under the chapter chemical bonding. It's a very interesting topic. It is about shapes of molecules. We often describe objects around us by their shapes. For example, a round table, the eggs are oval shaped, a square lighting. When we order birthday cake, we are very particular about the shape. Someone may like a round shaped cake, another person may like a step cake, and so on. Here is a photo of a pyramid shaped cake. So, shapes give good appearance to the objects. Not only that, they also give rise to important properties. For example, a round table would be more suitable in a small dining room compared to a square or rectangular table. Another example is, suppose we change the shape of the key, then it may not be able to open the lock. So shapes are very important. What about shapes in chemistry? We have learned that solids have a definite shape, liquids assume the shape of the container, and gases, they have neither definite volume nor definite shape. They just occupy the entire space available to them. So let's get deeper. What about molecules? Yes, covalent molecules do have molecular shapes or molecular geometry. VSEPR theory predicts the shapes of covalent molecules. It helps us to answer questions such as whether water molecule is having a linear shape or a bent shape. If it is linear, why? If it is bent, what is the reason? Now, boron trifluoride and nitrogen trifluoride have very similar chemical formulae but very different molecular shapes. What is the reason? A lot such questions can be answered using VSEPR theory. So let's explore VSEPR theory. Let's begin with the compound with which we are very familiar, that is water. We just can't imagine life without water. So it will be very interesting to know the shape of water molecule. The formula of water molecule is H2O. We know the electron configuration of oxygen and hydrogen. So applying octet rule, we can write the Lewis structure for water molecule. Okay. According to octet rule, an atom may share its electron in order to attain 8 electrons in its outermost shell or the valence shell. In case of hydrogen, it is 2 electrons. So oxygen atom shares an electron with each hydrogen atom, and each hydrogen atom contributes an electron towards bonding with oxygen. So there are 8 electrons around oxygen atom and 2 electrons around each hydrogen atom. So this is the Lewis structure for water molecule. Lewis structure shows the distribution of valence shell electrons of all the constituent atoms in the molecule. So it gives an idea about the chemical bonding in the molecule. However, it doesn't give any idea about the shape of the molecule. So let's have a closer look at the Lewis structure. So here the central atom is oxygen. So oxygen is the central atom because the other atoms, namely the hydrogen atoms, are bonded to it. Around oxygen, we can see that there are 4 electron pairs. Now these 4 electron pairs are in the outermost shell of oxygen atom. We know that it is the outermost electrons and the outermost shell which participates in chemical bonding. The outermost shell is also known as valence shell. So these 4 electron pairs are called as valence shell electron pairs. So there are 4 valence shell electron pairs around oxygen atom. Now we know that electrons are negatively charged. We also know that like charges repel. So there must be repulsion between these valence shell electron pairs around the oxygen atom. To minimize repulsions, the electron pairs will orient themselves such that the distance between them is maximum and thereby the repulsions are minimized. So the arrangement of the four valential electron pairs around the oxygen atom is like this. So here the line between oxygen atom and hydrogen atom represents the shared electron pair or the bond electron pair. The line also shows the direction in which the bond or the bond electron pair is oriented. Now the line between the oxygen nucleus and the lone electron pair shows the direction in which the lone electron pair is oriented. So this is the arrangement of valential electron pairs around oxygen atom in water molecule. If we consider only the arrangement of atoms in the molecule, we will arrive at the molecular shape or molecular geometry. So as we can see, water is having a bent shape. So it has a bent shape. The bond angle is 104.5 degree. So water is not having a linear shape. It cannot have a linear shape because there are repulsions between four valential electron pairs around the central atom. Due to these repulsions, it cannot have a linear shape. It is having a bent shape. So what do we learn from this example? Valential electron pairs around the central atom will repel one another. To minimize the repulsions, the electron pairs will orient themselves such that the distance between them is maximum and thereby the repulsions are minimized. And this gives rise to specific bond angles and molecular shape. So next, let us look at a more simple example. Beryllium chloride. So in beryllium chloride, the central atom is beryllium. Around beryllium, there are two valential electron pairs. Now there will be repulsion between these two valential electron pairs. They can minimize the repulsion by maintaining maximum distance between them. And that is possible when the angle is 180 degree. So beryllium chloride is having a linear shape. In case of beryllium chloride, around beryllium there are only two valential electron pairs. So it is able to have a linear shape. Whereas in case of water molecule, around oxygen there are four electron pairs, four valential electron pairs. So water is not able to have a linear geometry. So what do we learn from these examples? The number of valential electron pairs around the central atom determines the shape of the molecule. Okay. So having learned these 2 points, now we are ready to go through the postulates of VSEPR theory. So the first postulate, number of valential electron pairs around the central atom determines the shape of the molecule. Second postulate, valential electron pairs around the central atom will repel one another. To minimize repulsions, they will orient themselves such that the distance between them is maximum and thereby the repulsions are minimized. Third postulate, the valential of the central atom can be considered to be a sphere from which the valential electron pairs are projecting out. Also, the valential electron pairs are localized on the sphere. So, there is a definite angle between any two valential electron pairs. Fourth postulate, a multiple bond should be counted as a single electron pair. For example, in carbon dioxide, there are two carbon-oxygen double bonds. So the number of electron pairs around carbon are 4. However, while applying this theory, we must not count it as 4. We must count each double bond as a single electron pair. So the number of electron pairs around carbon must be counted as 2. Okay. Another example is sulfur dioxide. So in sulfur dioxide, there are two sulfur oxygen double bonds and also there is a lone electron pair on sulfur atom. Okay, so the number of electron pairs around sulfur are 5. However, while applying this theory, we must not count it as 5. We must count each double bond as a single electron pair. So The number of electron pairs around sulfur in sulfur dioxide is 3 and not 5. Okay. Now, fifth postulate. VSEPR theory is applicable to any canonical form of a given compound. Now, some compounds exhibit the phenomenon of resonance. They can be represented by two or more equivalent Lewis structures, known as the resonance structures or canonical forms. Now, VSEPR theory is applicable to any canonical form or any resonance structure of the compound. For example, ozone exhibits resonance. It can be represented by two structures. These two structures are the resonance structures or canonical forms of ozone, and VSEPR theory is applicable to any of these structures. So these are the five postulates of VSEPR theory. Now let us learn about the different types of valence shell electron pairs. Going back to the example of water molecule, we saw that around oxygen atom there are 4 valence shell electron pairs. Of these, 2 electron pairs are involved in bonding with the hydrogen atoms. So 2 electron pairs shown by black dots are involved in bonding. These electron pairs are known as bond electron pairs. So the electron pairs shown by black dots are involved in bonding. Since they are involved in bonding, they are known as bond electron pairs. Now the other two electron pairs shown by red dots are not involved in bonding. So they are called as non-bonding electron pairs or lone electron pairs. So around oxygen there are two bond electron pairs and two non-bonding electron pairs or lone electron pairs. Now let us look at methane. So the central atom is carbon. Around carbon there are 4 valence shell electron pairs, and all the 4 valence shell electron pairs are involved in bonding. There is no lone electron pair on carbon atom. So around carbon atom there are 4 bond electron pairs and there is no lone electron pair. Now how does it make a difference whether a valence shell electron pair is a bond electron pair or a lone electron pair? So let us examine each case. Okay. Now bond electron pair is shared between two atoms. It is under the influence of two nuclei. It occupies greater region or greater volume. So the charge density of bond electron pair is relatively lower. Whereas in case of lone electron pair, it belongs to only one atom. A lone electron pair belongs to only one atom. So it occupies a smaller region or a smaller volume. Therefore, the charge density on a lone electron pair is relatively higher. So, the charge density of a lone electron pair is greater than charge density of a bond electron pair. Consequently, the repulsion by a lone electron pair is much greater than the repulsion by a bond electron pair. So, we have this comparison. Repulsions between two lone electron pairs, that is lone pair repulsion, is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. So again we can see why water molecule is having a bent shape. So on oxygen atom there are two lone electron pairs. So there are lone pair repulsions, which is greater than lone pair repulsions, which are greater than bond pair repulsions. Okay, so the two oxygen hydrogen bonds are forced to bend such that the angle between them is 104.5 degree. So water molecule is having a bent shape. Now simple covalent molecules can be represented by the formula ABMEN. They can be represented to be of the type ABMEN. Okay, so where A is the central atom, B is bond electron pair around central atom, M is number of bond electron pairs around the central atom, E is lone electron pair, N is number of lone electron pairs on the central atom. Okay, so in case of water molecule, we saw that there are two bond electron pairs and two lone electron pairs on the oxygen atom. So water molecule is a Ab2E2 type of molecule. So it is B2 because there are two bond electron pairs and E2 because there are two lone electron pairs. Now let us look at phosphorus pentachloride. So the central atom is phosphorus. Around phosphorus there are 5 valential electron pairs and all the 5 valential electron pairs are involved in bonding. So around phosphorus there are 5 bond electron pairs and there is no lone electron pair on phosphorus atom. So phosphorus pentachloride is a Ab5 type of molecule. It is Ab5 type. So it is B5 because there are 5 bond electron pairs. So it is a Ab5 type of molecule. Now let us see how VSEPR theory predicts the shapes of different types of molecules. First, let us consider the molecules in which there are two valential electron pairs around the central atom. Now, such molecules can be of the type Ab2. Okay. First, let us look at the electron geometry. What is electron geometry? It is the arrangement of the valential electron pairs around the central atom. Electron geometry is the arrangement of the valential electron pairs around the central atom. So in Ab2 type molecule, there are only two bond electron pairs around the central atom. Now there will be repulsion between the two bond electron pairs and they can minimize the repulsion by maintaining maximum distance between them. And that is possible when the angle between them is 180 degree. So the electron geometry of Ab2 type molecule is linear. Okay. Now molecular geometry is the arrangement of atoms in the molecule. Now the arrangement of atoms will depend upon the arrangement of bonds or the bond electron pairs. So for Ab2 type molecule, the molecular geometry is same as the electron geometry. It is linear. Beryllium chloride, carbon dioxide and mercury chloride are Ab2 type of molecules. So now let us look at molecules in which there are three valential electron pairs around the central atom. Now such molecules can be Ab3 type or Ab2E type. Okay. So first let us look at Ab3 type of molecules. Electron geometry. Now there are three electron pairs around the central atom. The repulsions between them will be minimum when the three electron pairs occupy the three corners of an equilateral triangle. The central atom will be at the center of the triangle and the angle between any two electron pairs is 120 degree. So this geometry is described as trigonal planar. The electron geometry for Ab3 type molecule is trigonal planar. Now in Ab3 type molecule there are three bond electron pairs around the central atom and there is no lone electron pair. Now molecular geometry is the arrangement of atoms in the molecule. The arrangement of atoms will depend upon the arrangement of bonds or the bond electron pairs. So for Ab3 type molecule, molecular geometry is same as electron geometry. It is trigonal planar. So boron trifluoride has trigonal planar geometry. It is a Ab3 type molecule and the bond angle is 120 degree. So now let us look at Ab2E type of molecule. The electron geometry is again trigonal planar. For a given number of valential electron pairs around the central atom, the electron geometry is fixed. When the number of valential electron pairs is 3, electron geometry is trigonal planar. Whether it is Ab3 type or Ab2E type, electron geometry will be same. It is trigonal planar. In Ab2E type molecule, there is one lone electron pair and there are two bond electron pairs. So one corner of the triangle is occupied by lone electron pair and the remaining positions are occupied by the bond electron pairs. So this is the electron geometry of Ab2E type of molecule. If we consider only the arrangement of atoms in the molecule, we'll arrive at the molecular geometry. So as you can see, the molecular geometry is bent. It is having a bent shape. So examples of Ab2E type molecules are sulfur dioxide and ozone. Okay. So in sulfur dioxide, the bond angle is 119.5 degree. It is lesser than 120. In case of ozone, it is still lesser. The bond angle is 170. Now we may get a question in the exam, why the bond angle in sulfur dioxide is lesser than the expected bond angle. Now what is meant by expected bond angle? So for sulfur dioxide, the electron geometry is trigonal planar. When the electron geometry is trigonal planar, the expected bond angle is 120 degree. Okay. However, in sulfur dioxide, the bond angle is only 119.5 degree. What is the reason? Well, on sulfur, there is a lone electron pair, and we know that lone pair bond pair repulsion is greater than bond pair repulsion. So, due to lone pair bond pair repulsions, the bond angle in sulfur dioxide is lesser than the expected bond angle, or it is lesser than 120 degree. So they can ask a similar question about ozone. So in case of ozone, there is a lone electron pair on the central oxygen atom. Due to lone pair bond pair repulsions, the bond angle in ozone is lesser than 120 degree. So in case of ozone, the bond angle is 117 degree. So now let us look at molecules in which there are 4 valence shell electron pairs around the central atom. Now such molecules can be of the type AB4, AB3E or AB2E2 type. First let us consider AB4 type of molecule. The electron geometry is tetrahedral. The 4 electron pairs are directed towards the 4 corners of a regular tetrahedron. The central atom is at the center of the tetrahedron, and the angle between any 2 electron pairs is 109.5 degree. So this is the electron geometry for AB4 type of molecule. So in AB4 type molecule, all the 4 electron pairs are bond electron pairs, and there is no lone electron pair. Now, molecular geometry is the arrangement of atoms in the molecule, which depends on the arrangement of bonds or bond electron pairs. So for AB4 type molecule, molecular geometry is same as electron geometry. It is tetrahedral. Methane is a AB4 type of molecule, and it is having tetrahedral geometry with a bond angle of 109.5 degree. Now let us look at AB3E type of molecule. The electron geometry is again tetrahedral. So for a given number of valence shell electron pairs around the central atom, the electron geometry is fixed. It is, if the number of valence shell electron pairs around the central atom is 4, the electron geometry is tetrahedral. So whether it is AB4 type or AB3E type or AB2E2 type, the electron geometry is same, it will be tetrahedral. Now in AB3E type molecule, there is one lone electron pair and there are 3 bond electron pairs. Okay. So one corner of the tetrahedron is occupied by lone electron pair and the remaining positions are occupied by the bond electron pairs. So this is the electron geometry for AB3E type of molecule. Okay. Now if we consider only the arrangement of atoms in the molecule, we will arrive at the molecular geometry. So as we can see, the molecular geometry is trigonal pyramidal. So ammonia is a AB3E type molecule. It has trigonal pyramidal geometry. Now let us look at AB2E2 type of molecule. The electron geometry is again tetrahedral. So in Ab2E2 type, there are 2 lone electron pairs and 2 bond electron pairs. So 2 positions are occupied by lone electron pair and the other 2 positions are occupied by bond electron pair. So this is the electron geometry for Ab2E2 type molecule. If we consider only the arrangement of atoms in the molecule, we will arrive at the molecular geometry. So as we can see, the molecular geometry is bent. It has a bent shape. Okay. So water is a Ab2 E2 type of molecule. So in exam we may get a question like why the bond angle in ammonia lesser than the expected bond angle. So what is meant by expected bond angle? Now for ammonia, the electron geometry is tetrahedral. When the electron geometry is tetrahedral, the expected bond angle is 109.5 degree. However, in case of ammonia, the bond angle is only 107 degree. What is the reason? So in ammonia, there's a lone electron pair on nitrogen atom. And we know that lone pair bond pair repulsion is greater than bond pair repulsion. So due to lone pair bond pair repulsions, the bond angle in ammonia is lesser than 109.5 degree. It is in ammonia, the bond angle is 107 degree. Okay. Now they can also ask similar question in case of water molecule. Okay, why the bond angle in water molecule still lesser? Why is it still lower? It is lower than ammonia. It is lesser than 109.5. What is the reason? Okay, in case of water molecule, there are two lone electron pairs around the oxygen atom. So we have lone pair repulsions and lone pair bond pair repulsions, which are greater than the bond pair repulsions. So due to lone pair repulsions and lone pair bond pair repulsions, the bond angle in water molecule is further reduced to 104.5 degree. So now let us consider molecules in which there are 5 valential electron pairs around the central atom. Now such molecules can be of the type AB5, AB4E or AB3E2. First let us consider AB5 type of molecule. The electron geometry is trigonal bipyramidal. Okay, so the 5 electron pairs occupy the 5 corners of a trigonal bipyramid. The central atom is at the center of the trigonal bipyramid. Okay. In this geometry, there are two types of positions, axial positions, and this is the axial position, and the other type is equatorial position. Okay. There are two axial positions. There are two axial positions, and the two axial positions as well as the central atom are in a straight line. The two axial positions and central atom are in a straight line. Now the three equatorial positions are directed towards the three corners of an equilateral triangle. Okay, so the three equatorial positions are directed towards the three corners of an equilateral triangle. Also, the axial positions are perpendicular to the equatorial positions. So, an axial electron pair is perpendicular to equatorial electron pair. The angle between an axial and the angle between an axial electron pair and an equatorial electron pair is 90 degree. The angle between any two equatorial electron pairs is 120 degree. The angle between any two equatorial electron pairs is 120 degree. So this is the electron geometry. If we consider only the arrangement of atoms in the molecule, we will arrive at the molecular geometry. So in AB5 type molecule, there is no lone electron pair on the central atom. There are only bond electron pairs. Now molecular geometry is the arrangement of atoms in the molecule, which depends on the arrangement of bonds or the bond electron pairs. So for AB5 type molecule, molecular geometry is same as electron geometry. It is trigonal bipyramidal. So phosphorus pentachloride is a AB5 type molecule and it has trigonal bipyramidal geometry. So one question that we may get is why the axial bonds are weaker and longer than equatorial bonds. What is the reason? Axial bonds are weaker and longer than the equatorial bonds. Now we can see that each axial bond is perpendicular to three equatorial bonds. Each axial bond is perpendicular to three equatorial bonds. Perpendicular means the angle between axial and the three equatorial bonds is 90 degree. So, and 90 degree is small enough to cause high repulsions. So each axial bond suffers repulsions with three equatorial bonds. Consequently, the axial bonds are longer and weaker. They are longer and weaker than the equatorial bonds. So now let us look at AB4E type of molecule. So again, the electron geometry is trigonal bipyramidal. In AB4 E-type molecule, there is one lone electron pair and there are four bond electron pairs. Okay, so the lone electron pair occupies only equatorial position. The lone electron pair will not occupy axial position. It occupies, the lone electron pair occupies only equatorial position. The remaining positions are occupied by the bond electron pairs. So this is the electron geometry for AB4E type of molecule. If we consider only the arrangement of atoms in the molecule, we will arrive at the molecular geometry. So as we can see, the molecular geometry is seesaw. So if I turn this structure clockwise, it will resemble a seesaw. So this geometry is known as seesaw shape or seesaw geometry. Okay. Sulfur tetrafluoride has a seesaw shape. It is a AB4E type of molecule. Now let us look at molecule of the type AB3E2. Again, the electron geometry is trigonal bipyramidal. So in AB3E2 type molecule, there are two lone electron pairs and three bond electron pairs. The two lone electron pairs, both the lone electron pairs occupy only equatorial positions. Both the lone electron pairs occupy only equatorial positions. The remaining electron pairs will occupy uh, the bond electron pairs will occupy the remaining positions. Okay, so this is the electron geometry of AB3E2 type molecule. So if we consider only the arrangement of atoms in the molecule, we will arrive at the molecular geometry. So we can see that the arrangement of atoms resembles the letter T. So the shape is known as the T shape or the T shape geometry. So an example is chlorine trifluoride, which is a Ab3E2 type molecule and it is having a T shape. Now, why does the lone electron pair occupy only equatorial position? Why don't the lone electron pairs occupy axial position? So we saw this in Ab4E type molecule and also in Ab3E2. The lone electron pairs occupy only equatorial positions. Why is it so? So let us examine each case one by one. Why don't the lone electron pairs occupy axial positions in trigonal bipyramid geometry? Why do they occupy only equatorial positions? So first let us consider the Ab4E type molecule. Example, sulfur tetrafluoride. So there are two possibilities. There is one lone electron pair on the sulfur atom. So we have two possibilities. The lone electron pair occupies axial position. Okay, so when the lone electron pair is in axial position, it is perpendicular to three bonds. So perpendicular means the angle is 90 degree and 90 degree is small enough to cause high repulsions. Okay, now in case of structure B, the lone electron pair occupies equatorial position and it is perpendicular to two axial bonds. So the lone electron pair in structure B is perpendicular to only two bonds. Whereas in structure A, the lone electron pair is perpendicular to three bonds. So the amount of repulsion is less in structure B than in A. So structure B is the more stable structure in which the lone electron pair is in equatorial position. Okay. So now let us consider the Ab3E2 type molecule. Example, chlorine trifluoride. So there are three possibilities. There are two lone electron pairs on the central atom. So there are three possible arrangements. Okay. So in structure A, both the lone electron pairs are in equatorial position. Each lone electron pair is perpendicular to two axial bonds. Each lone electron pair is perpendicular to two axial bonds. Now in structure B, one lone electron pair is in equatorial position and the other lone electron pair is in axial position. So the angle between the two lone electron pairs is only 90 degree, and 90 degree is small enough to cause high repulsions. So structure B represents a very highly strained system, so we can rule out structure B. Okay. Now in case of structure C, both the lone electron pairs occupy axial positions. The angle between them is 180 degree. However, each lone electron pair is perpendicular to three equatorial bonds. So in structure C, each lone electron pair is perpendicular to three equatorial bonds. Whereas in structure A, each lone electron pair is perpendicular to only two bonds, the axial bonds. So the amount of repulsions is lesser in structure A. It is the least in structure A. So structure A is the most stable structure in which the lone electron pairs are in equatorial positions. So now we understand why the lone electron pairs occupy only equatorial position. The reason being that when they are in equatorial position, they are perpendicular to lesser number of bonds, and that gives rise to lower amount of repulsions and a more stable structure. Now let us consider molecules in which there are 6 valence shell electron pairs around the central atom. So such molecules can be of the type AB6, AB5E or AB4E2. Okay. First let us consider AB6 type molecules. The electron geometry is octahedral. So the 6 electron pairs are oriented towards the 6 corners of a regular octahedron. Okay. The central atom is at the center of the octahedron, and the angle between any two electron pairs is 90 degree. Okay. In this geometry, all positions are equivalent because the angle between any two electron pairs is same, it is 90 degree. So all positions are equivalent in the octahedral geometry. Okay, so this is the electron geometry. In AB6 type molecule, all the 6 electron pairs are bond electron pairs and there is no lone electron pair on the central atom. Now molecular geometry is the arrangement of atoms in the molecule, which depends on the arrangement of bonds or the bond electron pairs. So for AB6 type molecule, the molecular geometry is same as electron geometry, it is octahedral. For example, sulfur hexafluoride is a AB6 type molecule and it has octahedral geometry. Now let us look at AB5E type of molecule. So the electron geometry is again octahedral. For a given number of valence shell electron pairs around the central atom, the electron geometry is fixed. So if the number of valence shell electron pairs around the central atom is 6, the electron geometry is octahedral, whether it is AB6 type or AB5E type or AB4E2 type. The electron geometry will be same, it is octahedral. Okay. Now in AB5E type molecule, there is one lone electron pair and there are 5 bond electron pairs. So one corner of the octahedron is occupied by lone electron pair and the remaining positions are occupied by the bond electron pairs. Okay, so this is the electron geometry of for AB5E type of molecule. If we consider only the arrangement of atoms in the molecule, we will arrive at the molecular geometry. So as we can see, the molecular geometry is square pyramidal. So bromine pentafluoride is a AB5E type molecule. It has a square pyramidal geometry. Now let us look at AB4E2 type of molecule. So the electron geometry is again octahedral. In AB4E2 type, there are 2 lone electron pairs and 4 bond electron pairs. The 2 lone electron pairs occupy axially opposite corners of the octahedron, and the remaining positions are occupied by the bond electron pairs. So this is the electron geometry for AB4E2 type of molecule. If we consider only the arrangement of atoms in the molecule, we will arrive at the molecular geometry. So as we can see, the molecular geometry is square planar. So xenon tetrafluoride is a AB4E2 type molecule. Xenon tetrafluoride is a AB4E2 type molecule, and it is having a square planar geometry. So we saw how VSEPR theory predicts the shapes of different types of molecules, and we observed that for a given number of valence shell electron pairs around the central atom, the electron geometry is fixed. For example, if the number of valence shell electron pairs around the central atom is 4, the electron geometry is tetrahedral, whether it is AB4 type or AB3E type or AB2E2 type. The electron geometry is same, it is tetrahedral. Okay. The next point, when there is no lone electron pair on the central atom, molecular geometry will be same as electron geometry. For example, in AB4 type molecule, there is no lone electron pair on the central atom. So the molecular geometry is same as the electron geometry, it is tetrahedral. Third point, when there is one or more lone electron pairs on the central atom, the molecular geometry will be different from the electron geometry. Another important point to be noted is in case of trigonal bipyramidal electron geometry, if there is a lone electron pair, the lone electron pair will occupy only equatorial positions. Now suppose we are given the formula of a compound and we are asked to predict the shape of the molecule using VSEPR theory. How to do that? So here are the steps to predict the shape of a molecule applying VSEPR theory. The first step, write the Lewis structure. Second step, count the total number of valence shell electron pairs around the central atom. So in case of sulfur tetrafluoride, the number of valence shell electron pairs around the sulfur atom is 5. Now this gives an idea about the electron geometry. So in the third step, infer the electron geometry from the number of valence shell electron pairs around the central atom. So in case of sulfur tetrafluoride, the number of valence shell electron pairs is 5, which indicates that the electron geometry is trigonal bipyramidal. Next, count the number of lone electron pairs on the central atom. So in sulfur tetrafluoride, there is one lone electron pair on sulfur atom. Okay. If there is no lone electron pair on the central atom, say for some other compound, for some other molecule, there is no lone electron pair on central atom. In that case, the molecular geometry will be same as the electron geometry. Okay. And if there is one or more lone electron pairs on the central atom, then assign suitable positions for the lone electron pairs and remaining positions for the bond electron pairs in the electron geometry. So in case of sulfur tetrafluoride, the electron geometry is trigonal bipyramidal and there is a lone electron pair on sulfur atom. So the suitable position for the lone electron pair is the equatorial position, and the remaining positions are occupied by the bond electron pairs. So this is the electron geometry for sulfur tetrafluoride. So the next step, the sixth step is, if we consider only the arrangement of atoms in the molecule, we will arrive at the molecular geometry. So in case of sulfur tetrafluoride, if we consider only the arrangement of atoms in the molecule, we see that it is having a seesaw shape. Okay, so these are the steps to predict the shape of a molecule using VSEPR theory. So VSEPR theory is able to predict the shapes of a large number of covalent molecules, particularly in those in which the central atom is a p block element. However, the theory fails in case of many transition metal compounds. Also, the theoretical basis of VSEPR theory is not completely understood. It is not completely clear. Okay, so these are the two drawbacks of VSEPR theory. So now let us look at the important points that we learnt in this topic. The first point, repulsion between the valence shell electron pairs around the central atom gives rise to geometry of the molecule. Second point, the number of valence shell electron pairs around the central atom determines the shape of the molecule. Next, lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. Fourth, a multiple bond in a molecule must be counted as a single electron pair. Multiple bond, whether it is a double bond or a triple bond, it should be counted as a single electron pair. Next, we looked at the steps to predict the shape of a molecule using VSEPR theory. The first step is writing Lewis structure. Next step is counting the total number of valence shell electron pairs around the central atom. Okay, and the total number of valence shell electron pairs gives an idea of the indicates the electron geometry. So once we know the electron geometry, we should assign suitable positions for the lone electron pairs and the bond electron pairs. If it is a trigonal bipyramidal geometry, and if there is a lone electron pair, the lone electron pair will occupy only equatorial position. So the last step, consider the arrangement of only the atoms in the molecule. We will arrive at the molecular geometry. So these are the important points that we learned in this topic. So please let me know if you have not understood anything or if something is not clear or if you have any questions. So I have a list of questions here from this topic. So the first question, state whether each statement is true or false. Give reasons. So you'll be able to answer these questions if you have understood the postulates of VSEPR theory. Next, why is lone electron pair, the repulsion between lone pair and bond pair, greater than bond pair repulsion? So if you know the difference between lone pair and bond pair, you will be able to answer this question easily. So mention the type of molecule. An example is provided. Water is Ab2E2 type of molecule. Okay. So B represents bond electron pair around central atom. E represents lone electron pair around the on the central atom. So you can work out for the remaining molecules. Explain beryllium chloride is linear, but water does not have a linear geometry. Next, boron trifluoride and nitrogen trifluoride have similar formulae but different geometry. What is the reason? So the bond angle in each of the following compounds is lower than what is expected from electron geometry. Explain. So the bond angle will be lower when there is a one or more lone electron pairs on the central atom, and that happens due to lone pair bond pair repulsions. Okay. Next, predict the molecular geometry of phosphorus pentachloride using VSEPR theory. The next question is, in phosphorus pentachloride, axial bonds are longer and weaker than equatorial bonds. Explain. So if you know the geometry of the of phosphorus pentachloride, if you have understood the molecular geometry of phosphorus pentachloride, and if you know the bond angles, then you'll be able to answer this question. Predict the molecular geometry of the following molecules using VSEPR theory and justify the positions preferred by the lone electron pairs. So the molecules are sulfur tetrafluoride and chlorine trifluoride. Next, predict the molecular geometry for bromine pentafluoride and xenon tetrafluoride. The last question is methane and ammonia have same electron geometry but different molecular geometry. Explain. So these are the questions that I have for you. Please let me know if you are not able to answer any of these questions or if you have any doubts. Thank you.